Today I have the pleasure of introducing Mr. Jun Zhang, not Mr. actually, Dr. Jun Zhang. Dr. Jun Zhang is a scientist at the University of Miami, and he is also associated with the Hurricane Research Division of NOAA. He got his PhD in applied marine physics from Rasmus, University of Miami, in 2007. His research focused on hurricane boundary layer and dynamics, turbulence observations, and physical parameterizations. He has published over 70 peer-reviewed journal papers, and in the past 10 years, he has participated in HRD's annual hurricane field program, serving as scientist in Doppler radar, drop zones, and wind lidar experiments. Since 2012, he also served as a lead project scientist. He has flown over more than 30 hurricanes and and has experienced more than 100 IOL penetrations. So that's something commendable. He likes playing soccer, basketball, and he used to play video games, but I think that ended when he had kids. He likes Boulder, he loves the weather, the mountain, and I think the traffic also, right, is much better than Miami. So he's visiting DTC to finish his DTC visitor project, and he will give a brief update on his work. The title of his talk is Impact of Hurricane Physics on Hurricane Rapid Intensification Forecasts. So,
okay, thank you so much, Biswas. Can you hear me? Yeah. Good afternoon. Thanks for coming to my talk today. Today I'm going to show you, basically it's kind of like a report summary of my project funded by DTC's visitor program. Firstly, I'd like to acknowledge support from DTC, especially Biswas and Ivan. Also thanks Louisa for funding my project, Jessa for helping with my travel. I also want to thank some HWRF team members, especially Jun Zhang and Vijay, some of my HRD colleagues, and also collaborators. George is here, Dave Nolan, Mike Montgomery. I'm going to show some slides from collaborative papers and their result. Firstly, I'm going to look at the model physics impacts on hurricane rapid intensification forecasts. Here, RI is defined by 24-hour intensity increase by 20 to 30 knots or more. Basically, forecasting RI storms is still a big challenge for forecasters. And this is an example of Hurricane Lane. So this is the storm almost hit Hawaii this year. This satellite picture, you can see that this is the red line from the official HC forecast. And this is essentially the average of the forecast from different type of models. We have HWRF model, HMON from EMC, the large-scale models, FV3 model, for instance. You can see all these models forecasted lane to weaken after 36-hour forecast time. But in reality, if you look at the best track, you see the Hurricane Lane actually did a RI, rapid intensification. You see from Category 4 storm to Category 5 storm. Another example, this is Hurricane Earl, 2017. This storm almost hit my house. Actually, we got a Category 1 hurricane force winds of my house. Again, this is a very tough storm to be forecasted. You see all these numerical models, including the basin scale HWRF that's been developed at HRD now. You can see that all of them didn't forecast these RI events. And you look at all the forecast. This is the cycling forecast from HWRF. There's 2 RI events for Hurricane Irma. You see there's 2 cycles. So HWRF did forecast RI for this first RI period, but none of them forecasted the second RI. So there's still very difficult job for forecasters to give a good RI prediction at this point. So the objective of my project is try to evaluate how the model physics impacts the HWRF's ability of RI forecast, and also try to develop model diagnostic techniques to support model physics improvements. And here I'm looking at 3 components of model physics: the horizontal diffusion, Cumulus parameterization and boundary layer parameterization. Before I'm going to show you some of the results of HWRF analysis. I want to show you some of the early work. Actually, this is a Scott Brown Tau paper 2000. They run MM5 simulation of Hurricane Bob with different boundary layer schemes. This is the MRF, medium range forecast model, PBL, black tar scheme, Burke-Thompson scheme, essentially TKE scheme or box scheme. You can see that by running these different PBL schemes, they got a different intensity forecast in terms of both minimum sea level pressure and also the maximum intensity. And you can see the intensity can vary largely with different PBL schemes. And in their paper, they point out that skillful prediction of hurricane intensity change requires an accurate representation of boundary layer and parameterization of surface fluxes. And this is another paper, actually, Dave Nolan and I and Dan Stern, we did back 2009. So Dave, he ran WRF simulations of Hurricane Isabel by using two different PBL schemes, the YSU and MYJ scheme. We also changed the drag coefficients in the surface layer scheme. For instance, here the YSUD here is to change the drag coefficient formula based on Donnellan et al. 2004 paper. So you can see that with different PBL schemes and also drag coefficients, we got different intensity forecasts or simulations, and we also look at the structure and compare to in situ observations. So basically, here I just show you some examples from the sensitivity to the boundary parameterization. There are other papers that tested the other type of physics like macrophysics or cumulus schemes. This is an example showing you like why the model physics is important for hurricane simulations. And the question is like why we have to parameterize some of these physical processes, especially the subgrade scale physical processes. Here I'm taking a figure from George Brand's paper just published last year. What I'm showing you here is the spectrum of wind velocity, U here. So the y-axis is basically the spectrum or turbulent energy as a function of frequency. So George ran three different type of large eddy simulations. You see with 30-meter resolution down to 15 meter, down to around 8 meter resolution, and we compare this. The spectrum of wind velocity to the observations we took from the stabilized experiments, and you can see basically. So the higher the frequency, the smaller of the scales of turbulent eddies the model can resolve. So this data is actually 40 hertz, so we can resolve turbulent eddies with scale as small as 10 meter. But even running REI simulation with 8 meter resolution, we still underestimate the turbulent energy. So basically, this plot tells us that a lot of the physical processes, for instance, the processes with scale smaller than the model grid spacing definitely need to be parameterized. For the HWRF model with 2 kilometer resolution operational model, so basically they can mostly resolve this part of the energy. So I'm going to look at show you the impact of horizontal diffusion first on HWRF forecast. But before doing that, I'm going to show you some of the work George Brand did. Actually, this is the result from Brian Rotuno 2009. This right line curve showing the maximum axisymmetric tangential wind speed as a function of error h is the horizontal mixing length. George and Rotuno, they are the first to point out the importance of horizontal diffusion to the simulation of maximum intensity. You can see that as the error h increases, the maximum intensity decreases for both the axisymmetric 2D simulation, and also later on he ran his 3D simulations to get similar results. And in his 2010 paper, he recommended that RH equals about 1,000 meter is kind of the ideal setup for numerical models to match based on the climatology and also comparison with observational composites. So recently I did a paper with Frank trying to verify if HWRF model can reproduce some of George's results. So I ran 30 simulations using idealized HWRF model, also by changing the RH. So basically we confirmed what George and Rotuno found. So you can see that as we increase RH, we see decrease in the maximum intensity. Here, I run the HWRF simulation in like a forecast mode, the 5-day simulation basically, and look at the maximum intensity. And this is a little bit smaller than what George found in his model because he ran like 12-day simulation, I believe. And this is some work I did with Mike Montgomery by looking at the observations. So analyze data using some flight level data, 1 Hertz only for, at that time they did some low-level eyewall penetrations in some old storms, Hurricane Island, Hugo, and David. So I analyzed data. Essentially, we can directly calculate the momentum flux and then calculate the strain rate and the deformation, and backward calculate the horizontal mixing length. We found that on average is about 750 meters, even close to what George found based on his SAM1 simulations. And so for the operational HWRF, so for the 2016 version, so based on our observational work and George's papers, so we reduced RH from 1900 meters to 800 meters. So this is a clean experiment. Zach Zhang from EMC ran for me about 200 cases, running with the 2016 version HWRF, but changing RH based on the 2015 version HWRF. So it's clean experiment, same model, just change RH based on the coac parameter in HWRF. And you can see that by reducing RH, we didn't improve or downgrade much of the hurricane track forecasts. This is the intensity forecast verification. In terms of the intensity error, by lowering RH, we do see some more improvements in terms of the reduced intensity error, but this difference is not statistically significant at 95% confidence interval. At certain lead time, like 36 hours or 96 hours, the difference is statistically significant at about 80% confidence interval. And if you look at this is a scale plot, basically plotting the scale of intensity forecast for this 2015 setup and 2016 setup of RH compared to the 2014 version HWRF forecasts. And I mean, you can see that for both 2015 version and 2016 version HWRF with different setup RH, both models did a much better job than the 2014 version. We have 50% improvements, and by lowering RH, we improve the intensity forecast by 10 to 15%. Again, this improvement is only statistically significant at about 80% confidence interval. So, and the big improvement we found is actually for the bias. So, I mean, the intensity bias is definitely reduced from by reducing RH. You can see with the 2015 version RH, we have HWRF have a relatively large low bias, 8 knots, and by lowering RH, the bias is reduced. And also the storm size, in terms of radius maximum speed. So the HWRF tends to forecast larger storms than the observations. By reducing RH, we reduce the bias in terms of the storm size.
This is a 2 kilometer?
This is 2 kilometer model, yeah, operational HWRF. The 16, 8, and 2, 3 domains.
So just curious, in this year's HWRF, are they still using the default 1900?
But from 16, 17, 18, they're using 800 now.
Oh, they are? Okay.
Yeah. So after they changed, is there.
Okay.
Yeah. So we look at it, if the changing horizontal mixing length would impact the RI forecasts. So we did this contingency table. We have a total of about 400 cases, but you see this probability detection rate is really low if we use this 30-knot threshold, 30-knot intensity increase in 24 hours threshold. In terms of this score, the critical success index, there's not much difference actually. I mean, and also then we change to this a different threshold by lowering the threshold to 20 knots. It has increased in 24 hours. We do see some very about 5% improvement in this CSI score. But overall, I think by reducing RH didn't improve much in terms of RI forecast. So next, I'm going to show some analysis by looking at the impact of cumulus or convective parameterization on RI forecasts. This work has been done by DTC. Biswas have been leading this. In the past 3 to 4 years, DTC has implemented this Grail and Freitas scheme into HWRF, the GF scheme, and they did a lot of tests recently. This is slides from Biswas. He ran about how many cases here? 128 cases, and this is the track forecast. This is also a clean experiment compared to the SAS scheme. The SAS scheme is used in the operational HWRF. So both GF and SAS scheme are scale-aware schemes, but they have different setups in terms of the contribution to the total diabatic heating relative to the microphysics scheme. You can see that with the GF scheme, in terms of the track forecast, they actually show some improvements after 4-day forecast, and they show a substantial improvement in terms of the intensity bias too, like the horizontal diffusion. The bias is definitely reduced substantially by running the GF's Cumulus scheme compared to the control with the SAS scheme. And also Biswas and DTC, they did the RI verification. This with the 20 knots intense increase in 24 hours. Those are the numbers. This upper table is for the control. The lower table is for the GF run. You can, and I calculate this POD, false alarm, and the CSI scores. You can see with the GF scheme, they definitely have a better detection rate. They detect the heat case is 38, heat versus 28. I mean, the false alarm ratio is also increased a little bit, but the overall score is better. There's about 20% improvement in terms of this CSI score. So we try to understand why with the GF scheme, whether GF did a better job in terms of error forecast than the SAS scheme. So I'm looking at a case study. Thanks, Biswas gave me this case. They're also looking at the same case, but doing different analysis. For my project, I try to help them to do a dynamical analysis. Firstly, you can see for track forecast, there's not much difference between these two runs. Intensity-wise, the GF did much better in this case. This is than the SAS run. So firstly, I compare this 2 kilometer wind speed for this GF. Oh, there's no. Oh, here. Yeah, for the GF run compared to the SAS run. We have a P3 flight. We flew into Hurricane Gonzalo at 14:45 Z on September 15th. You can see at 2 kilometer, basically. GF scheme definitely GF run definitely did better in terms of the magnetic wind speed. Both run also capture the asymmetry of the wind distribution. But this is basically the intensity difference that caused this the better forecast of the structure. So I also look at the vortex scale structure. Basically, just look at the azimuthally averaged tangential wind speed, the top panels, and this RZ mean of radial velocity on the bottom panels averaged between 18 to 24 hours. So this is right before the intensity bifurcates a lot. Both runs, the storm tend to intensify, but you can see the structure in this GF run. The vortex is much deeper and stronger. You look at this, the contour of about hurricane force winds 30 meters per second. It goes to 8 kilometer altitude. But this one, in the GF run, in the SAS run, that the same contour only go to 4 kilometer. And in terms of the radial velocity, the peak inflow is stronger, in the GF run than in the SAS run. But interestingly, in the SAS run, we have a stronger outflow immediately above the boundary layer and also some stronger outflow in the outflow layer. Just look into some details of the low-level structure, inflow and outflow. You can see that definitely you see a stronger inflow near the surface and also a much shallower inflow layer depth for the GF run compared to the SAS run. You can see this is very interesting. The outflow, strong outflow above the inflow layer in this SAS run. One guess is maybe because of the difference in the distribution of diabatic heating in the SAS run, because the Cumulus parameterization contribution to the total heating is larger. It's smaller or larger? It's smaller compared to the macrophysics. So the heating induced secondary circulation above the boundary layer is weaker in the SAS scheme. That would basically couldn't compensate to this strong outflow above the boundary layer. So I also did an angular momentum budget analysis for these two runs. Again, during the spin-up time from 18 to 24 hours, this is the equation that we have this local tendency of absolute angular momentum, the mean radial advection, vertical advection terms, the eddy radial advection, eddy vertical advection term. This FR is basically friction term, the horizontal diffusion plus vertical diffusion. And you can look at the tendency. You can see in the GF scheme, we see this positive tendency. This black line is the radius of maximum wind speed RMW with height. You can see at low levels, we see a positive tendency spin up the vortex. In the SAS run, we do see some small positive tendency inside RMW, but mostly negative. So the main contributor to this positive tendency in the GF run is the mean advection. So basically, you can see in the boundary layer is larger than in the GF run than in the SAS run. For the total eddy transport, they're kind of similar, but at the above the boundary, there's slightly smaller for the eddy transport term in the GF scheme. So overall, basically the convergence of angular momentum offsets the dissipation of angular momentum due to friction. So that leads to the positive tendency in the GF run. And if you look closely over the convergence of angular momentum in these two runs, so the positive value means convergence of angular momentum. So you can see in this GF run is much larger than in the SAS run. So this is kind of consistent in terms of dynamics. That's why the GF run did a RI and this one didn't do RI. And then next I'm going to show you some of the analysis in terms of the boundary layer parameterization. This is kind of the focus of my work. This is in HWRF, we have this K-profile or KPP type of method to parameterize vertical eddy diffusivity. So Km is a vertical eddy diffusivity as a function of gamma is 0.4 constant, U star friction velocity, phi m is the stability function, and also basically varying with the altitude. In the 2011 version of HWRF, we have this original formula, but in 2012 version, because we found that the Km is really large in HWRF compared to my observations, you see these blue colors are the observations from Hurricane Island, Hugo data. Then we reduced the Km, it's much closer to observation, but not perfect in the 2012 version of HWRF by just changing this tuning parameter of alpha. It's not a physical parameter, but it's kind of did a good job. And then in 2015, Robert Falwell, he gave a talk here. He actually changed the alpha as function of wind speed by feeding the Km to my data, basically. So I'm going to look at the impact of just by changing the Km on the HWRF RI forecasts. So I have, this is from EMC, this is some clean experiment Yang Kwang ran back to 2014. I have about 200 cases, so I did this condition table. We have just look at the POD and the false alarm ratio, all those numbers. I mean, we can see by lowering the vertical diffusivity, definitely did a much better job, especially in terms of the score for the high KM forecast, the total score is 0.22, but we improved that to 0.62. There's definitely substantial improvement in terms of RI forecast, and we have a paper published last year by looking at the structure at the onset of RI. So in this paper, so basically what I did, I try to group the forecast from the low KM group and the high KM group. I look at the cases, the blue color lines, about 22 cases. In this high KM group, they didn't do RI, and compared to the low KM group, the forecast did RI. So this is a 30 knots threshold. And you can actually, interestingly, if you look at the intensity, the average actually before the RI onset, 12 hours before, the intensity average is actually very similar between these two sets of HWRF forecasts. So if we look at the structural differences, basically 12 hours before the RI onset. So we composited all the HWRF forecasts and look at the structure. So this is one of the example. So this is a boundary layer structure looking at the left-hand side are the results from high KM forecasts, and the right-hand from low KM forecast, and the upper panels from the tangential winds, axisymmetric tangential winds, and because this dashed line here is the height of the boundary jets. You can by lowering KM, you do see this reduce of PBL height, and also in terms of inflow layer depth, here the black solid line here, we see a much shallower boundary layer by reducing the vertical diffusivity. We also have a stronger inflow. In terms of thermodynamic boundary heights, there's not much difference between these two forecasts, but we do see a more unstable surface layer in this low KM forecast than in the high KM forecast. And then we also look at the composites, the inertial stability, and vertical velocity, and also divergence field, and the left panels from high KM forecast, middle panels from the low KM forecast, and the right panels are from the difference field. And you can see that when we lower the diffusivity, we do see stronger updrafts, axisymmetric updrafts inside RMW that's co-located with higher inertial stability. And in terms of the under the efficiency argument, and this type of structure would favor TC hurricane intensification. We also see like a low level, so there's a much stronger boundary convergence when we lower the vertical diffusivity. And this is just an example of my previous work. And during this DTC project, I focused on looking at a case study. This is two HWRF forecasts of Hurricane Earl 2010. Earl is an interesting case because Earl intensified actually in shear, in moderate shear. This is a 6 meter per second shear. So here I'm showing you the maximum wind speed, the intensity. So this case, the low KM forecast did a very good job compared to the best track, but the high KM forecast at the beginning, before 54 hours, you see there's a tendency to increase, but then the storm decreased and then weakly intensified. And here I'm showing the maximum at the mutually average tangential wind speed, and this is minimum as mutually averaged radial velocity. I mean, this is kind of following the intensity matrix George usually used in his papers. Look at you see much cleaner verification the evolution of the storm intensity. And here, this right-hand figure shows the shear evolution of the shear from both runs. I calculate the 850 to 200 millibar shear following the methodology, same methodology as in the shapes model, because there's not much difference in terms of the magnitude, shear magnitude, especially during the intensification period and before. So in this study, I look at the evolution of deep convection in terms of the convective bursts. A burst is defined as a grid point where the maximum vertical velocity is greater than 3 meters per second. So this is so what I'm showing you, this those crosses with the lines are the mean location of these bursts, and the thick black line is the RMW, radius maximum wind speed. For the high cam forecast on top, the low cam forecast bottom panel, and here this black line showing the bifurcation point in terms of the intensity forecast. And it's interestingly, we see that in terms of this convective burst, the mean location, it's about 6 hours before this bifurcation, you see the bursts tend to stay inside of the RMW in the low cam forecast, but they're actually located outside RMW, mostly in this high cam forecast. And just look at the burst counts before the bifurcation, 6 hours before the bifurcation points. This left-hand panel from the high cam forecast, the right-hand panel from low cam forecast. The upper panels are the burst counts as a function of R divided by RMW, radius divided by radius maximum wind speed, inertial stability, middle panels, and diabatic heating in the bottom panels. You can see that the majority of the burst is kind of inside our low-level RMW in this low cam forecast, or in this high cam forecast, the burst kind of outside RMW. And there's also some difference in the shape of inertial stability, and also there's a big difference in diabatic heating. You can see in the low cam forecast, the magnitude heating rate is actually larger than in the high cam forecast. It's also more concentrated inside RMW, that also is located at upper level altitude, extends to this 10-kilometer altitudes. While in this high cam forecast, there's a broader distribution and much lower values. And in terms of the energy efficiency argument, based on the paper, Dave Nolan's paper 2007, Jonathan's paper, and also recently Smith and Montgomery, they argue that using a different explanation for this location of diabatic heating, the relation between the location of diabatic heating and the intensification based on the angular momentum budget argument. So basically they were saying that if this heating is located further inward from RMW, then the heating generated secondary circulation above the boundary layer will offsize the radial outflow immediately above the boundary layer, so that helps spin up the boundary layer vortex. So it gives a different explanation, but nonetheless, our result is kind of consistent with these theoretical papers. So basically, varying vertical diffusivity can change the deep convection distribution and also the distribution of diabatic heating. And we also found some difference in terms of asymmetric distribution of the bursts. Right before the bifurcation points, you see at in the low cam forecast, we see a more symmetrically distributed convective bursts. Most of them we see inside RMW, and in this high cam forecast, all these bursts are mostly located in the downshear and down tilt direction. And recently, in some observational papers, Robert Rogers, we found in Hurricane Earl, and also Edward, basically from Doppler radar observations, that when the burst moves to the upshear left quadrants, that favor rapid intensification from observation point of view. I mean, this low cam forecasts the structure in this low cam forecast in terms of burst is more close, is more consistent with the observations than this high cam forecast. I also look at the vortex tilt evolution. So this is the tilt is basically defined as the displacement of the low-level center at 1 kilometer and the 8-kilometer altitude of some center. So this displacement is interesting. Actually, before this bifurcation point, you see this both forecasts show the relatively large vortex tilt, 40 to 60 kilometer tilt. And then before this bifurcation point, you see this vortex try to align to 10 kilometer with the tilt magnitude. But after this point, you see in the low cam forecast, the the vortex stay kind of aligned at about 10 kilometer. But in this high cam forecast run, the tilt did this oscillation. It's kind of did a precision. Tilted, try to align, and then tilted again, align again. So this is a very interesting result. So we look at the boundary thermodynamic structure between these two runs. The left-hand panels. This is the boundary entropy, basically equivalent parameter temperature. This is axisymmetric theta E in the boundary layer low levels. The left-hand panels showing the result from high cam forecast, and the right panels from low cam forecast, and the upper panels are before the bifurcation points, and the lower panels shows the result from the after the bifurcation points. I mean, look at the low cam forecast. You see before and after the bifurcation points, there's not so much difference in terms of the theta E, the low-level theta E fields. But if you look at this high cam forecast after the bifurcation point, you see there's a ton of low theta E air that will penetrate into the eye wall region. You definitely see the. I mean, this result is kind of in agreement with some theory of Michael Riemer. I mean, he basically pointed out that when the vortex tilt can induce tilt into downdraft in the outer core region, when the tilt is larger, that would flash more low theta air into the boundary layer. And also, you can see that from this horizontal view of low-level theta E, the 100-meter theta E from this high cam forecast, low cam forecast. And again, the upper panel is before the bifurcation, and lower panel after the bifurcation points. And you can see that in the low cam forecast, after the bifurcation points, the theta E increased a little bit through the boundary recovery, and but in this high cam forecast, even after, because the tilt become larger, so the theta E we still see the low theta E in the outer core region on this downshear left quadrants. So we try to look at if the surface fluxes can recover the theta E deficit for the air parcel moves from the upshear left quadrant to downshear right quadrants. So I did a simple budget analysis, basically by differentiating the equation of theta E, we get the tendency of theta E as a function of d theta dt and dq dt. Theta is the potential temperature, q is the specific humidity, and basically just looking at the impact of surface fluxes to this rate of the time change of theta and q, this latent heat flux and the sensible heat flux. So just look at the time after the bifurcation at 57 hours. So here what I'm showing you, again, the 100-meter theta E for high cam, in the high cam forecast, low cam forecast, and the black contours are the downdrafts. I only show the downdrafts. You see the low theta E is kind of co-located with the downdrafts. And this this green curve here is kind of inflow trajectory. We assume the air parcel travels from outer core following the inflow trajectory to the eye wall region. I mean, this is the shear direction. So on the downshear right direction, on the downshear right quadrant, usually convection is initiated. So we did this calculation trying to see if surface fluxes are enough to recover this theta E deficit with the increase of theta E from this upshear left to downshear right quadrants. And so basically for high cam forecast, the answer is no. So the surface flux, enthalpy fluxes are not enough to recover the observed theta E change. But for the low cam forecast, is actually the surface fluxes are actually enough to recover this theta E deficit. So to quickly summarize, in this project, I look at the impact of model physics on HWRF's forecast, especially for hurricane rapid identification, using the retrospective runs. We found that both the cumulus and boundary schemes have substantial impact on HWRF's RI forecast, while the impact of horizontal diffusion parameterization is small. The case study of Hurricane Gonzalo from DTC we compare the Gonzalo forecast from the GF scheme. With the GF scheme, we compare that to the SAS scheme. Definitely the GF scheme did a better job in terms of structure. For this case study of Hurricane Earl, 2010 case, by looking at the impact of vertical additivity on RI forecast, we found that KM not only changed the boundary structure, but also the vortex scale and also convective scale structure, and more importantly, their interaction with the environmental shear. So that there's a multi-scale interaction. It's kind of a chain of processes. So with lower vertical diffusivity, the inflow increased, and the air can move further inward into the toward the storm center, have stronger updraft. And when the vortex is stronger, then that's more resilient to shear. And then with smaller tilt, we have smaller, we have a less low theta air into the boundary layer, and then also with a stronger, deeper convection. So all these multi-scale interaction processes needs to be considered during a physics upgrade, because HWRF operationally is run with a cycling mode. So basically the initial condition from next cycle based on the structure from the previous cycle. So when we change all the physics, so they change the models, the structure, so that will change the whole forecast. So in the future, I plan to study another case from DTC, the Hurricane Edward case. But this is, I think, so you see the GF run did a better job than the SAS run. But we have a lot of observations in this case, Edward. So we flew multiple cases. Also, for this case, we have Global Hawk data, and also the Air Force data. At one time, I think here, about a 48-hour forecast time, we have 3 to 4 aircraft flying at the same time. So we can do some detailed comparisons between the H4 forecast with observations, and also, in collaboration with Biswas. And also, I'm going to look at some idealized simulations. Ivan Klina did it for me recently by running idealized HWRF with different type of HWRF schemes, including the YSU and MYJ scheme too. So I'm going to analyze these runs to look at how different boundary scheme will impact the spin-up dynamics and also the structure. So that's it. Thank you. Hi, Chris. Yeah. Oh.
If you can. Yeah. Interesting.
Chris, you can use the mic then.
Sure. So I'm more interested in the very interesting dependency on the diffusivity. So it seems like in the shear case, the tilt is more of a consequence of a weaker vortex, I think you were saying, right?
Yeah.
Have you tried doing similar experiments in a non-shear case to more fundamentally understand the vortex response to diffusivity? Case?
We did some idealized simulations by changing the KM, but we didn't look at the tilt. But that's a good suggestion. But we did look at beyond the vortex, the strength and size. So I also look at the static stability. So basically above the boundary layer. So this in terms of the tilt dynamics, like Porizer's work and Schechter work. So basically we found that after, it's very interesting, the static, the layer above the boundary layer is actually less stable in the low cam forecast. So in terms of the tilt dynamics, the Porizer's theory, Rossby wave damping mechanism, basically if you lower static stability, the Rossby dynamics, that's kind of favor the storm, the vortex will be more resilient when the storm is less stable. Yeah. So, but for a non-shear case, there may not be much tilt for both cases. But we'll take a look. Yeah. Thanks.
I'm having a hard time understanding how the convective parameterization scheme affects the results, and that's mostly just because I'm unfamiliar with convective parameterization schemes. So I was wondering if you could say what is it the convective parameterization scheme actually modifies? Does it just have a temperature and moisture tendency, or does it also modify the winds? In other words, do you get a velocity tendency from the Cumulus scheme?
Yeah, I'm not an expert either because I'm trying to help DTC to do them diagnostics. Maybe Evelyn, yeah, she knows more.
Yeah, there is a momentum mixing term from the convective scheme.
Do you have a sense for which?
Yeah.
Also, the GF scheme at 2 kilometers is basically a shallow scheme, isn't that correct? So basically, there isn't any deep convection when you run GF at 2 kilometers. It's just, it turns into a shallow scheme.
I mean, yeah, I know they look at the tendency of the cumulus contribution to the total heating. So the GF definitely has more contributions than the microphysics, right? Or
no, in the I think that time I was confused about what time you were asking. In the GF scheme, in the innermost domain, the microphysics is more active compared to the GF, but in the scalar SAS, compared in relative to heating between GF and scalar SAS has higher contribution. But in both cases, microphysics is more, but among GF and scalar SAS, GF has less contribution in the innermost domain.
Yeah, because I have a hard time trying to understand this structure. Like this one. So, I mean, for the GF scheme, you have a stronger inflow, but less outflow above the boundary layer. So this is very interesting. Because in my CAM runs, when I have like a stronger inflow, I always have a stronger outflow. So it's
I guess just a quick follow-up. When Rob Fauvel gave his summary talk here a few months back, he pointed out how the thermodynamics and kinematics were all coupled. You know, one affects the other and back and forth. I guess a follow-up question then, do you have a sense for how the GF scheme handles the hurricane near environment as compared to the SAS scheme? I mean, is it more moist or more dry? Or
it's more moist, yeah.
Okay.
This one is more moist, and the temperature is also warmer, right?
Warmer.
Yeah. Okay. So gives the diabatic heating, distribution is definitely different. Yeah, the Evelyn and the Biswas did a lot of analysis. I'm just helping them look at the boundary structure and the dynamics part of this project.
Thanks.
I just wanted to go back to the shear case, the Earl. If you can go back to the slide where you were showing like the crisscrosses where the convective bursts were. The next one, I think it is.
This one?
Yeah. If I'm interpreting that correctly, they both have the tilt direction in the direction of the shear as well. But I thought in the observe Earl, those convective bursts up shear happened because the tilt was pointing in that direction. So I was just wondering if you happen to know how you got those convective bursts up shear when the tilt is down shear.
So basically, I look at some of the low-level boundary layer structure. I don't know if that's can you explain that, but so I look at some of the asymmetric distribution of theta e and radial wind velocity. Okay. So you see at low levels, maybe below near the surface, you definitely see, especially the inflow, you see it's more symmetric in this low cam forecast than on this down. I think this is the shear direction. So the left of the shear is always have stronger inflow, down shear and down shear left. But then at low level, this is more symmetric. Maybe my guess is that because in the low cam case, the inflow is stronger, so that in all quadrants they try to penetrate inward of the RMW. But because the weaker vortex, you have this asymmetric distribution of radial winds, but they're weak, especially on this upshare set. They couldn't move inward into the RMW, so that the convection cannot be initialized there. maybe, yeah. Or the thermal is also maybe the thermodynamics may also contribute to that.
So maybe an interpretation could be that in the top one, maybe you have more of a dominance of shear versus in the bottom one, the low Km, you have both the frictional convergence penetrating farther inward together with the shear-induced asymmetries, maybe.
Yeah, that's kind of my thought. Yeah.
Any other questions, thoughts?
For Hurricane Michael, HWRF had forecasts that, compared to maybe the HWRF of 5 or 6 years ago, seemed shockingly good.
Yeah.
And I think that's a testament, to all these improvements that have been made along the way. But I was just curious if anyone's ever considered a formal attribution framework to try to look at the previous versions of the model and see the value of the changes and the improvements that have been made. If there's a way to apply, attribution framework to this problem, if anyone's thought about that.
Yeah, I mean but for EMC, they really change the model, but because they have it's understandable they have their operational pressure or requirements. So for each year they change different things, so it's hard to really isolate the impacts from a different type of physics. So I'm a research scientist, so I try to look at only the runs have clean change. So all these runs I look at I just change one thing. But for HWRF, you look at the 2018 version versus 2017. Yeah, they have improved, but you don't know like which one did the trick. So, but it's definitely is a good idea to rerun Michael with the previous versions. Maybe with the Cumulus scheme or other setup of physics to take a look. Yeah, Michael did it really well. So at the beginning, I showed the good cases. Actually, I have a slide. You see, they did very good for this one. HWRF somehow they did maybe only this cycle. I don't know, but it's a good run. I mean the official did better than official. Maybe overestimate a little bit. But definitely you see this RI and the weakening. Yeah. But for lane, I showed you, they did it pretty bad. How the model kind of weakened the storm.
Yeah, you went some, you lose some.
So it's still, this case, maybe there's not much shear. So for Michael, right, it's a low shear case? No. I think so. No?
Shear.
It's moderate shear.
It's moderate shear.
Yeah.
But it's very warm. The water is really warm.
Yep.
This is over the Gulf of Mexico almighty. So that maybe the ocean cooling, there's less ocean cooling. Maybe they did, yeah.
Yeah, I think, as Jonathan told, me and Jun thought about running idealized for different versions of HWRF, but at some point it was not compatible with the current WRF code. So we thought that, too much of work to, do the interoperability. So we abandoned that idea. Okay. Okay.
Just a general question, not for Jun, maybe somebody else in the room knows. What's the timeline at EMC or NOAA for moving to the FV3 base system and kind of phasing out HWRF? I'm just interested in.
Yeah, the global model. I think that VJ has a table.
I've seen the table. But it was too big. I don't remember the years.
2020 or 2021. I don't know. But they're talking about a unified modeling system.
Yes, yeah.
So basically one model,
yes.
Everything.
So it would be the FV3, global FV3 with a nest, basically over the Atlantic or east back. Okay.
So HRD got some funding helping them with the nesting, two-way nesting. I think Sujin or Gopo, they got some funding. Yeah. Or maybe, Luisa knows better.
I think it's yet to be determined whether they're still going to do like a parent domain with a nest within, or just the global model. There's a lot of money that's going into that, though, through the Harvey supplemental and various things like that. So our group will be working a little bit with that and trying to help transition over to that. But I think with the Harvey supplemental, they're trying to accelerate that pace that they do that transition.
And HWRF, is there a plan for HWRF?
HWRF is still running, right? I don't know.
I'm going to defer to my expert team. Comes up a lot, but
Oh yeah, she is.
But eventually, long term, as it will be phased out.
Yeah, I think that's the plan. Yes.
that's the plan.
I think as long as it's competitive, they'll keep running it. Like GFDL model ran for
20
until like a year or two ago.
Yeah.
Well, then they brought in
Right.
HMOM because NHC didn't want to give up its model diversity. So that's unpredictable. Because the NHC have a lot of say.
All right, thanks.
NCAR has a global model too, right? You have your own global model.
Okay. Thanks everybody for coming.
Yeah, thanks.